This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 6, Lesson 8, Quality 2, Process Capability, Yield, and Tolerance Stack-Up. Lesson 7 decided whether a process was in control. This one asks a harder question. Can it actually hold the drawing? We rate the process against the spec with CP and CPK. Use the normal curve to turn that into a yield or a defect rate, and then combine part tolerances two different ways, worst case and statistical. These are the deeper quality questions the exam likes. Concept 1, where Lesson 7 stops. The control charts told us the process was steady, but a steady process can still make scrap. So we add 3 tools that compare the process to the drawing. Capability, which asks whether the spread fits the spec and is centered. Yield, which reads how much of the normal curve falls outside the limits. And tolerance stack-up, which combines part tolerances across an assembly. One honest note up front. The handbook prints the standard deviation and the control charts, but not the capability indices, not a z-table, and not the stack formulas. So we derive each from the plus or minus 3 sigma idea, and anything the exam can't have you derive, it gives you in the question. Concept 2, Process Capability. A process makes parts on a bell curve about plus or minus 3 sigma wide. CP compares that spread to the spec width over 6 sigma. If CP is 1, the spread just barely fits. Industry usually wants 1.33 for a cushion. But CP ignores centering. CPK fixes that. It takes the distance to the nearer spec limit over 3 sigma. CPK is always less than or equal to CP, and they're equal only when the process is dead centered. So a big CP with a small CPK is the classic tell. Good spread, but the process has drifted off center. Neither index is printed in the handbook. They both fall straight out of the plus or minus 3 sigma idea. Setup. 1 process, 2 questions. A shaft with an upper spec of 20.10 and a lower spec of 19.90. So a spec width of 0.2 of a millimeter. It's running at a mean of 20.04, off the 20.00 target, with a standard deviation of 0.02. Where does that sigma come from? You estimate it from the range chart, R bar over D, with D from the sample size row. Now the same 5 numbers answer both the capability and the yield question. Solve. Capability and yield, same process. CP is the spec width over 6 sigma, which comes out to 1.67. The spread easily fits. But CPK takes the nearer limit, the upper one, over 3 sigma, and that lands at exactly 1.00. So the spread is capable, but the off-center mean dropped it to marginal. Now yield. The binding limit is the near one, and its C distance is the gap over sigma, which is 3. A handy link, that minimum Z is just 3 times CPK. The far limit is 7 sigma away, so it contributes nothing. The exam gives you the normal areas. The area beyond Z of 3 is about 0.1%, so roughly 1,350 parts per million fall out. And the benchmark worth memorizing conceptually, a centered process with limits right at plus or minus 3 sigma, loses both tails, 2,700 ppm, a 99.73% yield. Concept 3, Tolerance Stack-Up. When you stack several toleranced parts, the assembly tolerance combines 2 ways. Worst case just adds the absolute tolerances. It assumes every single part sits at its extreme at the same time. That's safe, but pessimistic. The statistical method, root sum square, treats the tolerances as independent spreads that partly cancel. So you take the square root of the sum of squares. RSS is always smaller than worst case. And it isn't a formula to memorize. It's the same root sum square quadrature the handbook already prints for measurement uncertainty. Just specialize to a plain sum, where every sensitivity is 1. Solve. Stacking 4 spacers. A bore holds 4 spacers, each 10 mm plus or minus 0.05, so a nominal stack of 40. Worst case just adds the 4 tolerances. 4 times 0.05 is 0.2, giving a band from 3980 to 4020. Root sum square squares each tolerance, sums and roots. The square root of 4 times 500 squared is 1/10, a band from 3990 to 4010. So RSS is half the worst case band. The shortcut for equal tolerances is T times root n, but it's only exactly half here because root 4 over 4 is 1/2. With unequal tolerances, you square each one and root the sum. Concept 4. Acceptance sampling. You can't inspect every part, so you judge a whole lot from a sample. The acceptable quality level is the worst defect fraction you'll still routinely accept. There are two risks in tension. Producer's risk is rejecting a good lot, consumer's risk is accepting a bad one, and the sampling plan trades one against the other. The operating characteristic curve plots the chance of acceptance against the lot's true defect fraction. A steeper curve tells good lots from bad more sharply. This one is conceptual on the exam. It's not a handbook topic, so there's no pill and nothing to look up. If a plan needs numbers, the question gives them. Traps. 5 ways this bites. 1. CP versus CPK. A high CP can still fail if the process is off-center. CPK is always the smaller one, so judge acceptability by CPK. 2. Worst case versus RSS. RSS is smaller. Don't add tolerances arithmetically when a statistical stack is asked, and don't RSS when it says worst case. 3. Plus or minus 3 sigma is 99.73%, not 100. It still leaks a couple thousand parts per million. 4. Population versus sample sigma. Capability uses the process sigma, while the sample formula divides by n-1. Match whichever the problem gives you. 5. Control limits are not spec limits. Capability compares sigma to the drawing. The chart limits came from the process. In control is not the same as in spec. Quick recall. Capability rates sigma against the spec. CP is spec width over 6 sigma. CPK uses the nearer limit over 3 sigma. Both derived from plus or minus 3 sigma, neither printed. Yield reads the normal curve at the binding Z, which equals 3 times CPK. A centered 3 sigma process is 99.73%, 2700 ppm, and the exam gives you the C areas. Stack up. Worst case adds the tolerances. Statistical roots the sum of squares and is smaller. Estimate sigma as R bar over D. The golden rule. CP is spread, CPK is spread and center. A process can be capable yet off-center, and a stack is only as tight as the rule you're told to use. Next up, Lesson 9, Corrosion and Chemical Processes. You can now rate a process with CP and CPK, turn a Z value into a yield or a defect rate, and stack tolerances both ways. Next we turn to how the material itself changes, the electrochemical cell, the galvanic series that ranks which metal corrodes, and the common forms of corrosion. Everything's at PEPrepengine.com. Cheat sheet, worked solution, and a quiz attached here.
The full study guide, with every equation and common exam trap, is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.